Welcome back. This is the Tutor Wizard. I'm Adrian. This is Willa. Please subscribe right here and right there. Yeah. Hit the notification bell. You'll get notifications for this series and a bunch of other ones. Yay! You're supposed to look like you wanted to do that when I do that. You look like my students have the time. Yeah, that face. What are we doing today? We're doing multivariable calculus. Chapter 2 is double and triple integrals. Specifically, now we're going to do 2.7, which is phrasing these triple integrals in cylindrical and spherical coordinates. Specifically, this lecture, what we're going to do is we're going to focus on what it looks like to describe objects in 3-space using cylindrical and spherical coordinates, and then we're going to look at the cylindrical and spherical volume differentials. And they change. Let's do it. So first, we're going to do cylindrical coordinates. It's basically polar coordinates in 3 dimensions. We're just adding a tautology, z equals z. So we have x is r cos theta, just like in polar. Y is r sine theta, just like in polar. And now z is z. Z is just the height. And we also have the helping conversions that we want. X squared plus y squared is r squared. The reason we're doing this, again, the bounds become much smoother when we translate everything from here. What we're now going to have is, then we'll have, remember, a will be less than or equal to r will less than b. Most of the time, you can change this r to be a general region of theta. Remember, we did in polar coordinates, which we can do here also. But at first, take it easy. And then you'll see that we're going to get alpha is less than or equal to theta is less than or equal to beta. I know those all look like Greek to you anyways, which some of them are and some of them aren't, Latin, Greek. But these are numbers, number. If we phrase it in another way, r squared is x squared plus y squared, so you could have horrible functions in x, y, or just have an r squared somewhere. And this is why we start switching to cylindrical for certain shapes. When we do that, quickly, we're going to do this in the last section of this chapter, 2.8. We're going to actually do change of coordinate systems and look at all the differentials if you do any change of coordinate system. And it's translated, this r comes from the Jacobian that's going to turn out when we do this. So we'll discuss this in greater detail in the next section and in videos to come. But for now, what we're going to do is just give you the volume differentials for cylindrical and spherical. And this is how we integrate in the change of coordinates. So if we want to change from Cartesian x, y, z, x equals x, y equals y, and z equals z, to x equals r cos theta, y equals r sine theta, and z equals z, the differential we're going to get is, because of the arc length subtended by a circle of length r and with angle theta, in this case it's delta theta, so the length s of this arc right here is not just delta theta, it's r delta theta, and that's where in this derivation where that r is going to come from. It's from the Jacobian. And then multiplying this volume of this differential box, or this, what is this now? A polar rectangle, I guess, or a polar box. Last time it was a polar rectangle, this time it must be a polar cube or a polar box. The volume of that is going to be length times width times height again, and then we cleverly figure out what those are, and this is where we get the cylindrical volume differential. Let's do an example of this. All right, example 1, let's find the triple integral of z over this region E, where E is the solid enclosed by the cylinder x squared plus y squared equals 4, but then bounded above by the paraboloid z equals x squared plus y squared, and below by the xy plane, which is z equals 0. So we have z equals 0, the xy plane down here is where we stop, and then we have the cylinder, but it's bounded above by this paraboloid z equals x squared plus y squared. So I already see that I'm going to have z is less than or equal to 0 is less than or equal to x squared plus y squared. But then I see I have that. If I put that in spherical, that's going to say x squared plus y squared is, or cylindrical, that's going to give me x squared plus y squared is r squared. So that could immediately give me r squared for my bound. And then when I look at this, it's nice to say that I'm going to have 0 is less than or equal to r is less than or equal to 2, and 0 is less than or equal to theta is less than or equal to 2 pi. 0 is less than or equal to z is less than or equal to r squared. And these are my cylindrical. Then what do I do with that? That says my triple integral over e of z dv. Z is z, so he stays, but everything else changes. This is the integral from 0 to 2 pi, the integral from 0 to 2, the integral from 0 to r squared of z dr, or dz, r dr d theta. Yes, it bothers you. These are all numbers, so you can technically move them. It's going to go in here. This is equal to the integral from 0 to 2 pi, the integral from 0 to 2 of r times 1/2 z squared evaluated from 0 to r squared dr d theta. this is equal to the integral from 0 to 2 pi, the integral from 0 to 2 of 1/2 r squared squared, and then I get another r, so r to the 5 dr d theta. I can split that if I want. I'm going to do that. This is the integral from 0 to 2 pi of d theta times 1/2 the integral from 0 to 2 of r to the 5 dr. This is equal to 2 pi, the first integral, times 1/2, which cancels nicely. And then I'm going to get 1 over 6 r to the 6 evaluated from 0 to 2. This cancels, this cancels. This gives me pi over 6 times 2 to the 6. There's a 2 in there, so I can cancel that. That's 2 to the 5 over 3, which is 32 pi over 3. Let's do spherical coordinates, then we'll do more. For spherical coordinates now, again, we're going to do this in the next section of this chapter when we do change of coordinates for any type of coordinate system. You're like, why would you want to do that? Because it's awesome. And then you get a Jacobian and you can carry around these differentials will be phrased in terms of a Jacobian. Right now what we're doing is, this is fairly new to you. This one, cylindrical, is a little bit easier because you've seen polar already somewhere along the line, hopefully. But now this one, what we're rephrasing is every point in 3 space, just like in the planar in polar, what we're doing is every point here you're used to phrasing as x and y, and then there's 2 pieces of information, and we're going to call the coordinate x, y. In polar, what we're going to do now in polar says, well, you can do that, but I need 2 pieces of information, but not the same 2 pieces of information. As long as I know the radial distance from the origin, and I know how far around I am in a unit, then those 2 pieces of information give me the same point in space. So I can describe every point in 2 space with Cartesian coordinates x, y, or every point in space, how far out do I go and how far around do I go. I can get any point in space with polar coordinates. Now we're doing the same thing with spherical. And now in 3 dimensions, what do I need? Well, I need that radius. We're going to call it rho, possibly just to confuse you because we like Greek, and not to be confused with the polar one, r. So I need a radius out. Then I need to be able to say how far around it I go. So I'm still going to have a theta that goes from 0 to 2 pi most of the time. But now I have to talk about up and down, which I didn't have to do in the plane. So now all we're going to reference is of the vertical axis, and I can go from 0, and phi is going to go from 0 to pi is what our bounds for these 3 general regions are going to be. So in general, we're going to have that 0 is less than or equal to rho is less than or infinity, some radius. And then we're going to have 0 is less than or equal to theta is less than or equal to 2 pi, and 0 is less than or equal to phi, not phi. Phi is less than or equal to pi radians. These are our general bounds for describing every point in 3 space now with 3 pieces of information called spherical coordinates, not x, y, z's. You can do this x, y, z, and you can also do it. P can be now, what were we going to do? R, theta, z, which was our cylindrical. Now we have 3 ways of phrasing the same objects, but some of them are much more convenient when we want to triple integrate and find volumes and all those kinds of things, centroids. Yeah, these ones are much more pleasurable to work with, and the bounds are nicer in certain scenarios. What is the differential volume for spherical coordinates in this derivation? Again, we're going to do this in the next section, but the picture sort of gives us, if we have now a spherical box, and we have 2 sides that are curvy, essentially, what we're going to do is, this one is the rectilinear one, that he's just the differential of the radius rho. But now we have 2 little differentials. If we use some trigonometry and derive these, or use Jacobians, we're going to find out that this guy is going to be equal to rho sine phi, a small change in theta. Remember, theta is going around and around this way, so it's a small change in theta. And then this one finally is the vertical phi goes from here to here, so he's the vertical one. So this arc length is subtended by that angle, which is going to be the radius rho times the small change in the angle, which is delta phi this time. Putting that all together, we got the differential volume, and we get rho times rho is rho squared, and then we have a sine phi, and we get that this differential is not just d rho d theta d phi. We don't sound as cool, and we don't sound like pirates anymore. It doesn't have quite the jingle. What is the differential? It's dv is rho squared sine phi d rho d theta d phi. Yeah, no jingle there. No jingle. Let's do an example. I really should have got the ice cream. Now I want ice cream, so we got to hurry up and finish this. This is literally the last scene. You're going to see me do my pitch at the end, and then I'm going to go eat ice cream. It's my daughter's birthday tomorrow. Ice cream! Find the volume of the ice cream cone bounded by the sphere. It's a perfect ice cream cone. You should see me make ice cream cones. Perfect spheres, perfect wedge cones. And then we got a waffle cone, which is the cone root 3z equals the square root of x squared plus y squared. I put the root 3 there so I could get a nice trigonometric value for myself. First of all, what does this look like in spherical coordinates? I'm going to guess that because I just did spherical coordinates and I just said, oh, let's do an example. What am I going to use? Probably spherical coordinates. What does that look like in this? Right now I have, what does this guy look like? This one's not so bad because we just get a conversion. We know that x squared plus y squared plus z squared is rho squared. And we're saying that's 1 squared. So that just says rho equals 1. So that's what a sphere looks like in spherical. Really easy. Why do you think we're using spherical coordinates? Because it makes the equations much simpler to integrate and do triple integrals and everything else. What's the cone? The cone is going to be root 3. And what is z? Remember, x is rho sine phi cos theta. Y is rho sine phi sine theta. And z is rho cos phi. So I'm putting those in here now. This is root 3 rho cos phi equals the square root rho squared sine squared phi cos squared theta plus rho squared sine squared phi sine squared theta. Oh, I can just smell a trigonometric identity. I have rho squared sine squared phi in both terms. I'm going to factor that out. That's going to give me the square root of rho squared sine squared phi times cos squared theta plus sine squared theta. Pavlov is already biting at the biscuit. This is going to be the square root. This is 1. This is the square root of rho squared sine squared phi. Technically, rho is positive, definitely, because he's a radius, and sine phi in here is going to be positive in our quadrant that we're in. We've checked. So this is going to give me rho sine phi. Still, I still did a little thing. I'm going to square root squared. And the square root of rho squared is absolute value rho. But I was like, he's positive, so don't worry, I can get rid of it. That's what I was doing every time, every time. Now that simplifies. That tells me that root 3 rho cos phi equals rho sine phi. So I can cancel rho first of all, and he's non-zero. And then I get what? Root 3 is equal to sine phi over cos phi, which is tan of phi. And that is going to tell me that my equation is going to be what? Phi is equal to pi over 3. That's the equation of the cone. Much nicer. And there's the practice of how to switch back and forth between rectilinear or Cartesian and spherical. Now we're going to use that information to describe our bounds and everything. What do we have now? Therefore, our bounds. This says 0 is less than or equal to rho is less than or equal to 1. This says that we're going all the way around because I want to eat the whole ice cream cone. I'm not cutting it. How do you can't share with Timmy. I don't want to. So everyone has to get a whole one, I guess. I'll figure out how to do that. And then what are we going to get? 0 is less than or equal to theta is less than or equal to 2 pi all the way around. And then 0 is less than or equal to phi. And we're going to stop at our bounds right here, which is this guy is phi equals pi over 3. So we have pi over 3. Oh, those look so, it's like numbers, numbers, numbers. Try and do that in rectilinear. Not numbers, I'll tell you that right now. Woo! And then what is that going to give us? That's now going to give us, and remember, x squared plus y squared plus z squared equals rho squared also all the time. Therefore, the volume of this object E, which is our ice cream cone, even we can put syncopated algebra. The cherry is not involved in there. The cherry's volume is 4/3 pi r cubed, where the r is the radius of the cherry. You can do that one at a different video. Eat the cherry first, then we're going to eat the ice cream. Gang. The volume of this is equal to the triple integral over E dv, which is best phrased in spherical coordinates. That's going to be the integral from 0 to pi over 3. Him first, because it's d rho d theta d phi is how I set this up. And then so the integral from 0 to 2 pi, the integral from 0 to 1 of, now what do we get? Don't forget the rho squared sine phi d rho d theta d phi. That guy's always going to be there. So now you're always going to be integrating. Hopefully you get 1 over a sine phi, because then it'll cancel. But you're always going to be integrating the phis finally for once. This is going to give me equals the integral from 0 to pi over 3, the integral from 0 to 2 pi. I'm doing d rho first. So that is going to give me sine 1/3 rho cubed evaluated from 0 to 1. Oh, I like that. You should see the bounds in Cartesian. D theta d phi. This is going to give me 1/3. This gives me 1/3 the integral from 0 to pi over 3, the integral from 0 to 2 pi of sine phi d theta d phi. These are now separated, so I'm going to. This is equal to 1/3 the integral from 0 to 2 pi of d theta times the integral from 0 to pi over 3 of sine phi d phi, which is equal to 1/3 times 2 pi times this one is negative cos phi evaluated from 0 to pi over 3. I'm running out of room, so I'm going to do it in my head. Don't do this. Wizards do it. Students write it down and use another piece of paper. I have 2 pi over 3. Cos of pi over 3 is 1/2, so I have negative half, 1/2 minus 1, which is 1/2, which is going to give me, coincidentally, pi over 3 is our volume of our ice cream cone. Units cubed, whatever that means. Is that larger than 1 unit or less than 1 unit? Slightly larger, 3.14 over 3. Yay, eat some ice cream. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and a bunch of other ones. I'll see you next time. I'm going to go eat ice cream.